So what we use now is we use what we call the system approach. When mechatronics, when the catchphrase mechatronics originally came out, basically what they were trying to do is combine mechanics and electronics. So that's why it got the name mechatronics, right? Mechanical electronics, which makes pretty good sense. But over time, mechatronics has become to include all types of disciplines, and these are just some. So what do we got up here? We got mechanics, we got electromechanical, we got control systems, we've got digital control systems, computers, even CAD. Even though we don't have time to teach CAD, we do have some CAD courses available that you can take. These all encompass on what we refer to as what? Mechatronics. Name Megaprint was originated in 1969 by C.G. Greer. What's his name? He was working with a Japanese company called Yaskawa, which is basically they are a big control system. Yaskawa makes the Motorman robots. That's one of the products that they make. We call it Motorman, but they're actually manufactured. Just about all our other robots are manufactured by the name of the robot. This is the one robot that the manufacturer has a different name than the robot. At the time, Yaskawa Electric Corporation was using some electronic features for manufacturing mechanics and mechanical solutions. So he wanted to introduce a term that would basically describe what these people have to do. So originally, mechatronics just dealt with electronics and mechanics, but it has evolved over a long time. And the problem is, it's becoming more familiar with people outside the trade, but it's still a term that a lot of people don't understand. So right now, if you went to Microsoft Office and you brought up Microsoft Word and you typed in mechatronics, it would tell you what? It's tell you spelled wrong. You could add it to your dictionary, so that's what we're talking about. So it's not even in dictionaries right now. So mechatronics is a catchphrase. We like to call it automated manufacturing. Just about everybody, you say automated manufacturing, they understand what you're talking about, right? You say mechatronics, they say, you do like Sarah Versa. So Sarah Versa came down and did this, and we was talking about mechatronics, and you know what she called it when she did that? Megatronics. A lot of people, they think big electronics, and they hear megabytes and stuff like that. So yeah, she did that on TV, Megatronics. So it's a multi-craft type trade, right? Pretty neat. This is the one that Stevens used, which is pretty neat. It's a pretty neat diagram. Control systems, control electronic systems, electromechanical systems, mechanical systems, mechanical CAD, computers, digital control systems. So all these are part of what we refer to as mechatronics. This is just another drawing. So what we teach is we teach what we call the system approach versus the traditional approach. So we used to teach what we call the traditional approach, which we taught how things worked. So we would teach you how an inductive sensor worked. We would teach you how a capacitive sensor worked. We would teach you how optical sensor works. We would teach you how transistors works. We would teach you digital. We'll teach you all these digital components. We'd teach you all that kind of stuff. And then at the end, we would try to put it together. What we do now is we do that opposite. We start off with the system, right? You understand? So here we'll learn about sensors. All we do is got just a basic feel of what the sensor does. When you take the sensor class, we'll get into more detail on how they work, right? If you take that class. Used to, we would teach the sensor class before we let you even get in here. But on the system approach, it's nice to know how they work, right? You understand. But once you understand how they work, then you get a better feel of what it goes to troubleshooting. But really, right now, we don't even need to know how they work. We need to know what they do. So if I say this sensor right here detects metals, then we're okay. How it detects it, right now, we don't need to know, right? You understand? And why we adjust them and stuff like that, we get into more detail. So we do what we call the system approach. So traditional approach, we used to start with what? The components, and then move to the system. The system approach, we start with what we did today. We start with the what? System, and then we move to the components later on. So if you take intro to PLCs, what you're going to do the first night, you're going to come over here and look at what the PLC actually does, right? You understand? When you take all these classes that are in the automated manufacturing, you're supposed to start out over here and do what we did today. Probably in a little more detail. I did it in a little more detail because this is really a really advanced class. But on PLCs, we focus mostly on what the PLCs do within the system. So this is the system approach. We start off with the system, then we move to the modules, then we do the application and components in the system, characteristic and design in the system, physical principles and characteristics, cause of the malfunction. So basically, the first half we're just trying to figure out how the system works, not the individual components, how the system works. And then the second half we'll move into the what? The troubleshooting phase. And then we'll end up back at the what? At the system. So we'll break the line apart. We'll assign a team to a module. The team will go out. They'll figure out how that thing works, right? You understand. Figure out the sequence it goes through. And but every time you're going to rotate modules, right? You understand. You're going to rotate modules and you're going to rotate teams. We okay? The basic system consists of electrical, fluid power, mechanics, and control. Everybody okay? So that's the basic system. So what we'll do is we'll start off with safety, then we'll move into the system. We should have done safety first, so I got those two back. Then we usually have a review, but this class right here, we're going to have to do a little more than a review. This is going to end up being a capstone class, which will be basically the last class. You'd already been introduced to the system several times, but here's where we actually try to teach how to troubleshoot it, right? All the other classes will come over and just see what a system is and basically how it works. Here we're going to have to do a little more about its electrical and power and mechanics because while we're trying to set the course up, we're going to teach the course a little different, which means we're going to sacrifice a little bit of troubleshooting and stuff that we would normally get out of the way in this class. Then we're going to cover electrical, fluid power, soldering. So y'all learn about soldering in this class, and a little bit about a PLC. And we don't do the MC3. We don't do the certification anymore. Originally, what we did was when we got certified to do NC3 meter certification, we decided to put it into DC, but we had a lot of people that was through with DC. So what we did is we made that part of this class too. So we sacrificed one whole class to do meter certification. But hopefully, if you hadn't did the meter certification, then what we'll try to do is just try to do an off-class type introduction. Of that, so everybody can hopefully get that certification. But this is the layout of the system. Are we okay? Everybody okay? Okay, so what's the first thing we're going to start on? Second. Well, and more. So there's some neat videos on there on safety. And originally, we had OSHA, right? OSHA's been around for a really long time. And then we had what we call the National Electrical Code. Anybody familiar with NEC, National Electrical Code? What is NEC? What is it? What is it? I mean, so you get this big old NEC book, but what does it cover? Well, what it covers is how to safely install equipment. And what they realized right off the bat is that it did not cover your safety. But normally, if you safely install something, then that usually deals with your safety. There's nothing in NEC that indicates how you're supposed to use a step ladder. There's nothing in NEC that says what type of meter you should use. There's nothing in NEC to say you need to watch out for slippery things. So there's really nothing in any National Electrical Code that tells you what you need to be safe, right? So National Electrical Code covers the safe installation of electrical equipment. That's what it does. Wire gauges, how do you run wire gauges, temperatures, stuff like that, how to install stuff safely. And is the National Electrical Code, is that law? It's recommendations. Now, it can become law, but it's up to what we call the authority having jurisdiction, whether they accept the National Electrical Code or not. So every time the National Electrical Code comes out, it comes out every 3 years. Then these authorities having jurisdiction, like the electrical inspectors in the city of Birmingham, they have to adopt the code. If they don't adopt the code, then it has nothing to do with us, right? You understand that? And usually, it takes the National Electrical Code is so dang big that usually most authorities have a jurisdiction is one code book behind anyway. So when 2005 came out, right, you understand, Birmingham was probably still using 2002 for quite a while until they could go back and do what? See what changes were made before they adopted. So what they did is National Electrical Code decided to come out with a safety code that covers your safety around electrical equipment. By the way, NEC is published by the National Foundation of, the National Fire Protection Association, NAFTA. Unfortunately, we have a National Flood Power Association, and they go by the same acronym too. So when you see NAFTA, it's not necessarily National Fire Protection. It could be also National Flood. So what in the National Electrical Code is the 70 standard. It's NAFTA 70. But just about everybody knows it as what? The National Electrical Code. 70E, this is electrical safety standards. And this, guys, has changed a lot of stuff. Even though OSHA does not say it, they've adopted a bunch of the standards that are in the 70E standard. Now, this covers your safety around electrical equipment. And they've did some things that really, really have changed. First of all, they've identified a voltage level which they say above could be potentially lethal, and below is not potentially lethal. Anybody know what that voltage level is? 50 volts. So anything above 50 volts, now below 50 volts, we still have to use standard personal protection equipment, which everybody usually calls PPE, right? You understand that? So above 50 volts, things change. Below 50 volts, basic protection. What's the basic protection you think? Leather gloves. If you're working on not even really. If you're below 50 volts, you don't have to wear leather gloves. Below 50 volts, you still have to have glasses, safety glasses. You still need to wear fire resistant or clothes. You can't wear synthetic clothes, right? You can't wear open-toed shoes, right? You understand. You can't wear short pants, and that's just basic. Shoes are supposed to be leather shoes, by the way, but we let y'all get by. Tennis shoes are really good too. But normally, if you go to work, you'll have to wear at least leather shoes. And then other companies have other safety standards. Like if you work for U.S. Steel, you got to wear steel-toed shoes or metal tarsal protection. So not only do you have to have steel-toed shoes, you got to protect the top of your foot. I'm laughing because you get used to those things, and you get out there and you want to set something heavy. You put your shoe on there and you set it down on your shoe, and then you pull your shoe off. And then you get home in your tennis shoes and you forget you don't have your steel shoes on. That sounds like the voice of experience it is. But anything above 50 volts, that's where we got to start dealing with things. And then we do what they call an energy level verification. Depends on what type of PPE you have to wear. So it depends on where you go to. And just about every company around here basically deals with what? With the 70E. In fact, a lot of people train on that. Are we okay? The 910, we're supposed to have a book out here, but Nancy stuck it somewhere and I'll have to find it. The 910 is a OSHA standard, and it's got every standard in there, the 1910, that OSHA recognizes. And this book is about this thick. subpart S inside the 1910, and I'll have to find it and let y'all look at it. This deals with electrical safety. And what you'll find, just about everything in 70E is going to be inside the OSHA standard. Now, OSHA is an international standard, right? And by the way, OSHA is not, it's only if you do interstate commerce that you are required to meet OSHA standards. So what they're saying, basically, if you manufacture stuff in your community and it's kept in your community and you're not an international organization or national organization, you don't ship across state lines, you're still not responsible for OSHA. But what's nice about OSHA is that if you meet the OSHA standards, then it's going to be extremely hard for somebody to sue you, right? You understand that? 70E, we're going to talk about 70E requirements. We're going to talk about electrical safe working standards, understanding arc flash hazards. So what 70E is, it's added safety standards that basically guards you against shock. People say electrocution, but if you get electrocuted, that's not going to be good. You can't get electrocuted until you get shocked. So 70E don't specify electrocution standard. It says what you need to do to prevent from getting what? Shock. And then also something that we refer to as arc flash and arc blast. Now, that's the main thing that kills most people. They either get shocked or electrocuted, or they get blown up by what we call an arc blast and arc shattering. Also understands arc flash hazards, categories of PPE. Everybody understand what PPE is now? Safe approach boundaries. So what you end up with, anything you get above 50 volts, they have to do an energy available or energy standard. How much energy is available? You know, so we might have 120 volts that's protected by a 100 amp breaker, and that would maybe have more stringent safeguards than, you know, 400 volts protected with a half amp breaker, right? You understand? Fast blow. So they do an energy capabilities analysis on your system, and this determines the PPE that you have to wear, and it also understands what we call the boundaries you have to wear. So we have different boundaries, safe approach boundaries in different places, and of course the closer you get to these high energy, the more types of PPE you have to wear. This was in 2010. 1,734 electrical related workplace fatalities in 2003 to 2010. 13,150 severe injuries. 80% of all these injuries were caused by what we call arc flash. So that's a pretty good deal. So that's one of the things they wanted to really specify when the 70E standard came out. Anybody understand what arc flash is? Arc flash. So what happens is, and I don't know if this is going to record or not, guys. I have it set up to record. If not, the videos are going to be up there. That don't look good. Okay. One of these pictures might not work. Body electrical resistance depends on, it's not a fixed quantity. Not only does it depends on the thickness of your skin. It depends on if you're sweaty, if you're not sweaty, right? You understand? If you got any cuts, depends on the path, hand to hand, hand to foot, foot to foot, hand to elbow, etc. Depends on whether you're wet, whether you got open, or you got AC. DC, the problem we have with DC is DC wants you to latch on to things. DC, when you grab onto something and it contracts your muscles, you can't let go. AC, we still run into that problem, but AC goes to zero we're using 60 cycles here, which means Alabama. This is not Alabama Power. This is TVA. That goes to 0 volts 120 times a second. So sometimes you can get out of it. AC is more dangerous if it goes through your heart, because what happens is your heart works off of electrical pulses. Your heart cannot beat 120 times a second, and that's what AC tries to make it do. It tries to make your heart beat 120 times a second, right? You understand that? Your heart can't do that, so it goes into what we call fibrillation. What's fibrillation? It means your valves and your heartbeat is out of sync. Your valves are opening when they're supposed to be what? Closing, or closing when they're supposed to be opening, and you don't build up any blood pressure. So your blood starts flowing in your body. And if you don't get blood to your body, then you got big problems, right? So that's why we use that. What's that? It's not a defibrillator, it's called the shock thing. Yeah. They bop your heart, one big shock at the same time, and it tries to make everything do what? Come back into sync. Yeah. So electrical current paths, we've already looked at that. And these are the paths that are potentially legal. Touch potential, step potential, touch potential. Are we okay? This one I found this on the internet, which is pretty neat. It tries to give you a basic look at the different resistance you have in different locations. And what I thought was neat was ear to ear, they say we have an average of what? 100 ohms, yeah. Dry skin, though, is pretty high, 600,000 ohms. Hand to foot, 500 ohms. Wet skin drops things down, so it all depends on a lot of stuff, how much current you get in your body, right? I found that on the internet too. These are electrical shock effects, which I thought was pretty interesting when I was researching this, in that women and men have different thresholds of pain, which is pretty neat. So here, a man, the average for a man on DC is they can start feeling it on around 1 milliamp, and women can start feeling around 600, about 600 microamps. I guess they come up and hook people up. What's that one on one of the Ghostbusters? Ghostbusters. I think it's the second one where what's this guy? He's got a real beautiful woman in there, and got this guy sitting over there, and he asks some questions, and he's got shocks hooked up to him, and if they answer it wrong, he hits him. And no matter what the girl says, he says she's right, and he always shocks the other guy. So it's fun. So anybody that tells you women are more sensitive than men, this basically proves it, right? So I guess it's kind of like a hearing test. So they put you in a booth, and they give you different sounds, and you hit a little button when you hear it. So odds are what they did is I don't know. That's a good question. You can see AC as a little less sensitive. We have a little less sensitivity to AC than we do DC, because of the constantly going back to what? To zero, which is pretty neat. So I thought this was pretty neat. And also, the higher the frequency, the more dangerous it becomes. Which is pretty neat. So at 10,000 kilohertz, I wouldn't feel it until I got about 7 milliamps of flow through my body, which is pretty interesting. So these are our two electrical safety standards, the 1910, which is OSHA. Well, the OSHA, and like I said, I don't know where Nancy put it. I have to find it. but it's about that big, and it covers all the safety standards that OSHA covers. So OSHA is safety in the workplace. So it's got sections in there for carpenters. It's got sections in there for just about any trade you could go into, right? You understand? But subpart S, that's the part that covers electrical safety. So is OSHA law.
Sorry, boy, where's he at today?
We got the honor of having the compressor in our room. Can't find the 1910 book. It's around here somewhere, guys. Nancy didn't know where it was at, so she didn't put it up there. So OSHA is a law, right? You understand that? But National Electrical Code is not a law. It only becomes law what? If the authority having jurisdiction adopts it. Is NAFTA 70E, is it law? No, right? Could be. Yes, for employees of the so if you're an employee of the Department of Energy, it is law. If you're not, then it's going to have to be what? Adopted. Everybody understand that? But I don't know of any manufacturers in our local area that has not adopted 70E. So National Electrical Code is a regionally adopted standard for the safe installation of electrical wiring and equipment in the United States. Everybody understand that. 70E is the standard for electrical safety in the workplace. It's a standard by the National Fire Protection Association. The document covers electrical safety requirements for employees. Are we okay? And this is the book. We got one of these guys around here somewhere. But this link is also available up there. And this takes us into the Department of Safety. So this is the soft version of the 1910 policy. And so we're looking at section what? Yes. So you can see this thing is used, isn't it? And they've left space in it. It's kind of strange where they've got one that's not quite ready yet. So we'll see that when we get there. So all these numbers down here are what? Reserved. So introduction, electric utilization system, general, wiring and design protection. And then you'll get into this, right? That makes sense? Everybody okay? That makes sense? So there's the soft version. And like I said, I'll put a link up there. I think there's one on Blackboard. If there's not, I'll make sure it gets up there. So, you know, you could go up there and peruse that if you wanted to. And these are the parts right here. So, subpart is electrical. The 301 to the 308, this is safety installation. This is the one that we would be interested in. 331 to the 335, these are what? Work practices. And then the 399 is nothing but what? Definition. And then let's see if we can find those. Did it put me back to the spot? Yeah, it did. Okay. I think what that's it. So here we go. This is not the PowerPoint's on Blackboard. Of course that. This isn't, but there should be a link on there. It should have a link. It should have an internet link. So if you wanted to actually go through there and look at it, it should be. I was trying to figure out how to get back into it again. Yeah, so this, I just got back. So these are all the actual safety standards down through here. You see that? So when we upload the PowerPoints, we do it as a PDF, what we call a PDF file, a professional document format, and none of the links work inside that. So normally if we got links inside the PowerPoints, then I try to put them inside there, but sometimes I forget. Qualified workers. So what's a qualified worker? What is it? What is qualified?
Someone who's certified to work on.
Yeah, ones that receive training and has demonstrated skills and knowledge in the construction and operation of electrical equipment and installation and the hazards involved. So that's what they define a qualified person as. Are we okay? Employees who face a risk of electrical shock that is not reduced to a safe level of installation equipment must be what? Trained. So all we're doing is just touching on the high points of this. So anybody in this occupation, and it's on the next slide, must be trained. Other employees if they face risk of shock. So these are the list right here of people who must be trained. And what I've got in red, that's us. So electrical, electronic engineers, electrical, electronic equipment assemblers, electrical, electronic technicians, and electricians. These guys have to be trained in electrical safety. You understand that? So when I went to work for U.S. Steel, basically they came in and they threw me in with, when I was what do they call that? They don't call it apprentice, they call it something else. So they basically just put you with somebody that knows what you're doing. Now, from what I understand, if you get hired, the first week you go through safety. You go through safety orientation at U.S. Steel. So it's changed a lot. There's a video too, I wish I could find that one, where the guy talks about how he was trained. It's basically the way I was. But where the guy said, you don't want to do that. Training focuses on recognizing live parts, determining voltage of live parts, and clearance distance specified about. And the clearance distance basically is specified by how much energy is available. So a lot of these places you'll see these lines on the floor where we go through different zones. No. 33, so this basically just covers basically what it covers. Focuses on working your exposed energy and potentially energy parts. Blocking and tagging, which is what we're going to do. De-energizing, verifying de-energized condition. And people don't understand that. So when you go out and lock out and tag out, there's a lot of people that takes for granted that they've taken away power from everything. So one of the things you're supposed to do is verify that everything's been de-energized. So what do we normally use to verify things have been energized? Try it? No, we don't do that. What do? We have these things we call voltmeters. So we check things with voltmeters. So we're required, I think, in this class for you to have your voltmeter, right? You understand? So anytime you lock out stuff, or we use gauges. So if it's pneumatics or hydraulics, we use pressure gauges. And this is why just about every pneumatic and hydraulic lockout has a pressure gauge on it. Unfortunately, they don't put voltage meters on there because they depend on you to have one. So one of the first things you should do when you lock out and tag out, number one is you lock out and tag every energy source, right? You understand? Anything that has stored energy, you're supposed to release it. Now, what's nice about our lockouts on our pneumatics is that it not only does it lock it out, but it also dumps the pressure. So what you'll see is our pressure gauges, when you pull that lockout, it goes to 0. If you got one that when you pull it out and the pressure gauge stays up to this, then you got to drain that pressure off, right? You understand? So this is why we have a pressure gauge on every one of our units over there. But what you'll see on those, you'll see those drop down. So that's something you're supposed to look at. If the pressure gauges are available, you make sure you verify that they're setting on 0, right? Especially on these devices that we can store energy on.
Can you just lock out something or tag out?
No, you cannot. You can have a tag without a lock, but you can't have a lock without a tag. So what a tag does, so they are not the same. Tag out and lockout are not the same. A tag just specifies information. So I might say, so that would be like the custodians here, when they put that yellow thing out, it says wet floor. So it just conveys something that you need to be cautionary about. A lock, when we put a lock on a thing, we have to specify why that lock's on there, who put it on there, right? You understand? So that is required. So we used to carry the actual tags. So we use the actual tags. One company that we was talking about, they actually have a picture of themselves on there. So their tag is on their lock. I think U.S. Steel puts a little brass thing on there now that puts your employer number, I think, or employee number on there. Is that right? What? Not a U.S. Steel. U.S. Steel. Okay. So that way, that means they can identify you. The only person that removes a tag, a lock and a tag, is who put it on there. Unless you go through some very stringent steps where they've got to make every attempt possible to get you out there to take your tag off. And then they have to get permission from you if they cut it off, they have to get permission from you to do it. And you can understand why they do have things in sequence. I put a lock on this thing, and then I go off to Illinois somewhere, right? You understand? And they've got to get that machine going, so somebody else comes in there and fixes it, but they can't legally remove your lock unless they get permission from you to do it, right? So they don't have to get in contact with you, but they've got to do multiple methods of trying to get in contact with you before they cut that lock off. And they have to document why they did that, right? You understand that? Re-energizing. There's a lot of places that have procedures that you have to go through to re-energize stuff. So a lot of times you just can't turn something on. You have to go out and turn things off, put the lock off, re-energize it, and then go and energize things in different methods. And that's what you'll have to do. Overhead power lines, clearance and distances, illumination, and several other tasks you have to make and ensure. And that's what we cover inside this section of the 1910. Are we ready? Are you okay? De-energized parts, live parts that which the employer may be exposed to, shall be energized before employees work on or near them, unless the employer can demonstrate that de-energizing introduces additional or increased hazards or is feasible due to equipment design and operational limitations. Live parts that operate less than 50 volts to ground need not be de-energized, but there will be no increased exposure to electrical burns or to the explosion due to electric faults. So it doesn't say it's safe to work on 50 volts. It just says there can't be any other potentials in there, right? Now there is a clause that allows certain people to work on live equipment, and that's us. Because you can't troubleshoot something without it working, right? You understand? Use of equipment, portable equipment, plug-in cord equipment, reclosing circuits and inspection equipment. That's what that section covers. PPE, are we okay? Most used when exposed, maintenance and inspection, insulation tools. Insulated tools, too. So a lot of times you get into these high energy equipment, not only do you have to protect, but you also got to protect your tools. Are we okay? This is 70E. Father, it didn't tell us the exception. There is an exception in this for this standard right here, and that is if you troubleshoot. If you're a troubleshooter, because when we troubleshoot on normally on live equipment. Everybody understand that? But if we're going to repair, if you're going to do maintenance on the equipment, then the equipment has to be what? Locked and tagged. Everybody has to be de-energized, locked and tagged. Everybody okay there? 70E, a lot of people, this is what 70E covers. Electric shock, arc flash burns, thermal burns, and arc blast. What do you need to avoid getting these problems right That's what the 70E covers. So does it cover electrocution? No, it covers shock. Well, like we said, you cannot be shot, you cannot be electrocuted until you get shocked, right? And we don't like getting shocked. Electrocution is real bad, but getting shocked is bad too. Arc flash, electrical short circuits that occur when arc flashes from a exposed conductor. The problem is, as soon as you get a little arc across there, electrical arcs create something we call ozone. Ozone has a very low resistance. So that's what an electrical arc does, creates an ozone. And you can smell it too sometimes. Used to on laser printers, before they put, laser printers works at a real high voltage and uses that technique. And before they've started putting filters on there, carbon filters, you can smell that laser printer. You can smell the arc in there, which is really neat. It's a real funky smell. But as soon as it arcs and creates that ozone, then what it does is it creates a low resistance path. And then what happens now? Now you create a sure enough arc, right? You understand? Moving through air, which has a pretty good deal of resistance, right? Creates a lot of heat real fast. Are we okay? And then an arc blast. What is arc blast? Yeah, it's a pressure wave that's caused by an arc flash. And there's all kind of videos up on YouTube that talks about arc blast and arc flash. Arc blast, concentrated energy floated outward, high intensity flash. Temperature, I was wrong. I said 32,000 degrees. Temperatures can reach 35,000 degrees. A pressure wave can reach 200 pounds per square inch. So that's 200 pounds per square inch. So if you come up here and calculated my area, that would be how much force is generated against my body. So if I moved it against a square inch, that's 200 pounds. 2 square inches would be 400 pounds, right? You understand? So you can imagine this blast coming out and hitting you. And the first thing it's going to make you do, it could crack ribs. It could crack ribs or break ribs, right? Could cause us to, normally it causes us to breathe in real fast, right? And there's really nothing you can do about that. It's just a natural reaction. Vaporizes conductors, and this is the problem we have with an arc blast, is not only do you have that heat, you've also got all this molten stuff moving at you, right? Conductors, they go into vapor instantly, and all this garbage is moving in. Arc flashes cause severe burns, severe broken bones, vision damage, hearing damage, loss, brain trauma, punctures and lacerations, and of course could cause loss. Yeah. So even if you got all that PPE on, you know, you still could end up with this right here. Everybody understand that? What you're going to get away from all this burn and all this breathing in all this garbage that's coming at you. Causes of arc flash. Number 1, improper training. Number 2, improper work procedures. Drop tools, and this is why insulated tools come into play. Accidental contact with electrical system. Installation failure. Inadequate short circuit current ratings. And voltage testing with inappropriate equipment. We got one, they don't show the guy, video that we show. It's about a guy called Eddie. And they had a system that had failed. And he went into a power room and was testing a 2300 volt surface with a regular meter. Went in there by himself, which is also against all rules. So usually you work with 2 people, right? You understand. Went in there by himself, put that meter across that thing, and it blew up on him, created an arc blast. And they said he came out and he was on fire. And people saw this fire moving down there. They didn't understand what it was, but it's Eddie walking around down there. And they traced his path. His clothes was falling off of him. Where he touched stuff, his skin would bleed, and of course he passed away. And they did that video as a memorial to him because of what happened to him. But whose fault was it? It was his. He didn't use the right test equipment. He went in there by himself, right? Buildup in dust can cause this. Corrosion or insulating in surface and improper maintenance, sparks produced during racking of breakers. Y'all understand what racking a breaker is now, right? This is when they actually take that big old breaker, and you think about the little circuit breakers you have at your house. These commercial breakers, they're going to be in big square boxes. They're going to be about that deep, got extremely big insertion plugs on the back, and you literally set those things on a rail, and they bring them out on a cart, and they raise the cart up so it's even, and they roll them out, right, put them on that cart, go and work on them, and then they bring them back, slide it in, then they engage it with a screw, and then they crank that screw and literally rack that breaker back into its spot. No. And then they don't do it right. So that's why they came out with different methods of racking. And one of the things they do is you can put it in there and then do what? Close and latch that door and then rack it from outside, which that guy didn't do. We looked at racking a breaker, right? I don't know what this one is. We'll see what this is. Oh, this one has audio. What time does this class go to for? Huh? 1:30. It's going to take me a little while to get back in sync with the class.
This particular night, things were pretty normal.
Hi, I'm Frank Block. I'm the Electrical Superintendent at Anglo American Door.
So if y'all would rather have